Okay, 3.3 again, nonlinear regressions. We're going to take a look at power regressions. We kind of just threw it into the last example right at the end. That's okay. Formally, power regressions produces equations in this form, okay? So y equals ax to the exponent b. Here's an example. For a physics project, a group of students videotape a ball dropped from the top of a 4-meter high ladder, which they have marked every 10 centimeters. So 10 centimeters, and remember this is the distance in meters, so it's going to be a little bit scaled there, okay, because we're going from centimeters over here to meters. Okay, during playback, they stop the videotape every 1/10 of a second and compile the following table for the distance the ball traveled. So let's take an actual look at this and let's decide, does this fit the linear equation well? And then let's apply the power regression, find the curve of best fit, and then decide, does the curve of best fit with the power regression or does the linear regression work better with this data? Okay, and then we're going to do a couple predictions with the regression curve. Okay, so all you need to do is sub these numbers in. Let's go to 11. Okay, so again, highlight these, view, nope, data, insert. There we go, scatter plot. Okay, make sure that the scatter plot is highlighted. I'm going to go quick layout, okay, because the quick layout gives us everything, including the linear trend line. So this is ball dropping, okay, and this is going to be time in seconds, and this is going to be distance in meters. Okay, so here's the linear trend line. Now, does this do a good job? Me personally, I don't think so, because I see this curving up and I see it continuously curving up and increasing faster. So let's actually add a trend line. So let's go, sorry, trend line, more trend line options. Okay, we get this. So what we're gonna do is, I had to X this and then just go to more trendline options for this to appear. So we're actually going to do power this time. Okay. So this is the power regression. So instead of exponential, this is power. Okay. So which one is a better fit? And then let's go, how long will it take to fall 10 meters? And then how far would the ball fall in 5 seconds? That should be question marks. Okay. So for our power, we're going to display the equation and display the R. Okay. So we're going to put it right down here. So is this a better fit? I'm looking at this. It pretty much hits every single point, and it's veering up so that it goes with the flow of data. Okay. So now what this wants us to do is it wants us, so I'm going to say the power regression is a better fit. And now let's actually just sub these numbers in. So the first question, how long, so let's predict how long the ball would take to fall 10 meters. Okay, so we know that the height equals 10. So let's just plug in equals 4.8075 times 10 to the power of 1.9916. Let's see. Yes, so what this is not reading is that I didn't put this multiplication symbol in it. So yes, let's correct it. Okay, so How long will it take? 471. Height. Nope, this is wrong because height is 10, therefore the y is 10. Sorry about that. Okay, so this would be, I'm going to calculate this per hand. Y equals 4.8075. Okay, so what we're going to do is we want to sub in the height, which is 10, equals 4.8075 x to the 1.9916. Okay, so in order to get the 4.8075 out of the right-hand side, we divide it out. 4.8075. Okay, and what are we left with? 10 divided by 4.8075. I get 2.08008, 3203. And that still equals x to the 1.9916. So without using methods and functions, I'm just going to use a grade 11 method. So what we have to do is we have to do change of base. So we have to find a number when we raise it to the number 1.9916, it will give us the number 2.800,83203. So some number, and we have to have the exact same exponent. So all I do is I literally pick up my calculator and I'm going to start with 1.9916. Okay, gives me 3 too big. I'm going to do 1.5 to the exponent 1.9916. Okay, so all I've done so far was do 2 to the 1.9916. Okay, and that was too big. That gave me 3.9. I did 1.85 to the same number, and it gave me 2.2. So this is too small. So it's somewhere between the numbers 1.5 and 2. So let's go 1.8. Too big. 1.7. Too big. 1.6 is too small. So let's go 1.65. Okay, let's go 1.65. Okay, to whatever 1.9916. I get 2.711. So we're getting closer. Okay, I'm going to be happy with this. 1.68 approximately. Okay, so 1.68 to this equation equals this. So we can get rid of those. We know that x equals 1.68. So it takes 1.68 seconds to drop a height of 10 meters. Now, let's take a look at this. Last question. It asks us predict how far the ball would travel in 5 seconds. That one is the easy one. That one is when we go equals 4.8075. Put that multiplication symbol in. We said 5, correct? So it would take, how far would it travel in 5 seconds? It would travel 118 meters. And I believe that's it. Distance in meters, time in seconds. Yeah. That's it.